So angle of declination is what basically it is the angle between geographic meridian and the magnetic meridian at any point on the Earth's surface. Suppose if this is the point P, and I say this point P is basically the where you need to find out the angle of declination, and this thing is basically the geographic meridian. On this geographic meridian, there will be which poles to be lying? Which poles will be lying on the geographic meridian? The true North
Geographic
Pole and
north
the true
and
South
south.
Pole, right? And let's say at this particular point, this is basically another plane which is passing through. On this plane, what will be lying? On this plane, what will be lying
Magnetic
somewhere?
north
The
and south.
magnetic north and the magnetic south, right? So basically, this angle which is there between both of them, this is basically the magnetic meridian. So this angle between both of them is basically called as the angle of declination, right? Here, generally it is denoted by delta,
Yes, sir.
or it you can denote it with some other symbol, whatever you like. So suppose if Earth is there, and I'll draw these two planes. Let's say I'll draw this plane, and there will be some North Pole over here, South Pole over here, and let's say the point P is lying over here somewhere, right? So if I have another plane which is like this, acha, thoda sa maths, I'll be using a little bit of maths, okay? Tell me this particular thing. If I have what do we call it? If I have two planes, right? And if I have two lines, suppose, and these two lines, can you see the point of intersection of these two lines is basically a point, right?
Yes, sir.
So whenever two 1D lines are there which are intersecting at one particular point, so this concept you already know, right? So similarly, when two planes are there and these two planes are passing through each other, then the point of intersection, it won't be a point of intersection, it will be a line of intersection, right? Yes or no?
Yes, sir.
So always remember ki if two lines are cutting, then they will meet at one particular point, and if two planes are cutting each other, then they will meet at a if two lines are there, then these lines will if there are two planes, these two planes will meet over a line, and that is what we are drawing trying to draw. Control C, Control V. But can you see this point, the geometrical south, the geometrical north, and the geometrical south all should lie on this plane? So can you see this point P is common in both the planes? This is the point P, and if I try to intersect, then this will be the line of intersection. It will be lying on both. थोड़ा सा 3D में डायग्राम है, try to understand line of intersection between geographic meridian and magnetic meridian. Can you see point P is lying on the line which is common in both of them? Or let me just copy a diagram from internet. Wait, don't draw. Two lanes intersecting in a line. Can you see, guys, this particular thing now? Can you see this particular thing, guys? Guys, can you see the figure? Can you see the?
Yes, sir.
This will be basically the line of intersection between the AB, the line AB. The point P will lie on this AB, right? Can you see one plane, which is basically MN plane, right? It will contain the geographical north somewhere, and it will contain a geographical south, whereas this plane will contain what? This is a rough diagram, you don't need to draw it, na? This is not for school purposes, this is just for understanding purposes. Okay, this will be the magnetic north and this will be the magnetic south. Can you see this particular thing? Everyone, is it clear? Now is it clear, guys, what exactly I was trying to draw? In your schools, how will you draw this particular thing? You will not draw the other section. Can you see this part where you will not draw? You will just draw this M, this line AB, and that part of the other one. So basically, whenever you have this particular thing, you will just say this. This is basically your what? This is your geographic meridian. And if I have one more, then this will be your magnetic meridian. Is it clear, guys? And this angle will be known as the angle of declination. Basically this. Is this clear, guys? Are you understanding the concept now? Okay, what exactly is happening? Is it clear? Can you see this point P is lying in the magnetic meridian as well as the geographic meridian? So basically, can you see both are what? Is this clear? Guys, hello.
Yes.
So this should be the point P where you define that. This line should go towards geographical north. And clear? Now, assume this, guys, on a sphere. Assume the same point on a sphere. Can you see when I change the longitude at different points, the value of this angle will be different, right? Yes or no?
Yes, sir.
So, some points about angle of declination. Note the first point. The angle of declination will be different at different points on Earth's surface. Achha, have you drawn till here, guys? Have you drawn this diagram as well? Everyone drawn this diagram as well, so that understanding purposes? It will be much more easier to visualize like this, right? Is the first point clear of note and note?
Yes, sir.
Sir, where is this angle of declination is used? See, for example, suppose you are in merchant navy or you are a sailor, suppose, है ना? So you decide that you want to reach the true north, right? Then we know this particular fact कि whenever I have a magnetic needle, that magnetic needle will always point towards the, where will the magnetic needle will point always towards? The needle will always point towards the magnetic north. So if a sailor wants to move to actual or true north, acha, if the sailor keeps on following the magnetic needle blindly, then will he be reaching the geographical north? Will he be reaching the geographical north or will he be reaching the magnetic north? Yes or no? Tell me. Will he be reaching magnetic north or will he be reaching the geographical north? If I am following a magnetic needle blindly, I am not considering the angle of declination. I am just considering the magnetic north, the needle, right? So if I keep on moving in the direction of the needle, then automatically I'll reach towards the magnetic north, not the geometrical north, right? So if I want to move towards the actual north or basically the geographical north, then we need to shift the direction by certain angle, right or wrong? If I keep on moving in that direction, then can you see at different points this angle will be different. So if I don't consider this angle, I'll reach the magnetic north. I'll not be able to reach the geographical north, right? So we need to shift the direction by a certain angle. Also, please remember this angle varies with different position of latitude. Okay, so this angle keeps on varying. So basically, with respect to your position, you need to keep adjusting this angle to reach the actual north, right? Reach the geographical north. And this angle is nothing but what? Which is basically just basically our angle of declination. Is this clear, guys? Where exactly is it used? And
Yes,
sir,
sir.
how do we know the angle of declination at one particular point? You can know the angle of declination very easily with the help of this thing. I think generally it is used to measure the horizontal component of it, but still there is a chart. Always remember that people have already done this analysis for you, and whenever you will see a chart of or a map of the world, then you will see at different points they will basically mention the different angles. They will mention the latitude, longitude as well. That is one for geographical positions, and to find out the actual north, they will mention the angle of declination at different points. So all of this it's there. Anyways, uh, third point: if the object moves on the surface of Earth then the magnetic needle will point towards the horizontal component of Earth. Right? So suppose if this is your Earth and this guy is, let's say, over here in a boat standing with a compass. So do you know this particular thing now? If he is at this particular position, then the compass will point towards the magnetic north, right? Yes or no? If I zoom into the picture, will it look like this? Yes or no? Yes or no, guys?
Yes, sir.
And at that particular point where he is observing the magnetic field, will the magnetic field will be going like this? Because it's the what? In the North Pole, we know this particular thing, magnetic field goes into the Earth's surface, right? So here, if I say this will be your BH and this will be your BV, then the magnetic needle will point in the direction of BH. Can you see? Is this clear, guys? Can you imagine the whole situation in front of you? Everyone able to do it? Right? Yes or no, guys? Is this clear? And please
Yes, sir.
remember one more, remember this, it will always point towards the horizontal component of Earth. Also, the needle, if I want to talk in terms of the plane, needle will align itself in the horizontal magnetic meridian. So just like a line can be broken into two components, even a plane can be broken into two components, right? So the horizontal component of that magnetic meridian, the needle will align itself in that direction. But anyways, this is much more simpler. So I guess these points are pretty much clear to you. Everyone understands what is the horizontal component of Earth. Everyone understands what is the angle of inclination and angle of declination, right? Yes, sir.
Yes, sir.
Yes, sir.
So if someone asks you what are the three elements of Earth's magnetism, so what are the three elements which are responsible, or basically if you know these three elements, then automatically you can predict the direction of Earth's magnetic field. The first is basically the horizontal component of Earth, right?
Yes, sir.
The second is basically the angle theta, basically angle of dip or inclination. And the last one is basically delta, which is the angle of angle of declination. Okay, so if you know these 3 points, then automatically we can predict the direction of Earth's magnetic field. Is it clear?
Yes, sir.
Sir, I have a doubt. In the angle of declination, we drew two diagrams, right?
Yeah.
Like two planes, and how we in the first diagram it shows like south, magnetic south is on the top and magnetic north is on the bottom. How are we able to like show it in this the second
In this diagram?
No, this one.
This one?
The plane, yeah.
So
We're showing both on the same right? Like magnetic north and magnetic south and geographic north and geographic south. In this before diagram, isn't it like the planes? How are we able to show? We are showing this part of the plane, right? Like 1/4 of the diagram,
we
right?
are just showing only that part which is coming out. Can you see only one part of half of the plane?
Yes, sir,
in
but
this.
how are we showing it as magnetic north and magnetic south?
I
And
have taken any point in the northern hemisphere where this northern hemisphere we know this particular thing. I told you about what I told you this particular thing. If I have taken any point on the Earth surface, but generally for references I take it in the northern hemisphere. So that is why I'm saying if you consider Earth like this, can you see Earth? Let me draw the Earth for you. Earth surface. So if this is the Earth's surface, can you see if this will be the plane in which the north and south pole will be north and south pole will be like this? Yes or no?
yes,
The
sir.
diagram is not accurate, and even this figure is not accurate. But can you see in this particular plane only this north pole and south pole will lie somewhere? I'm not telling you this is exactly the position of north pole. I'm not saying this is the position of north pole and this is the position of magnetic north. This is the position of geographical north. I'm not saying like this. I'm saying like this ki on this part, on the upper side of the plane, somewhere this will lie, and on the downside will somewhere this geometrical south will lie.
Oh, okay, sir.
Okay, these are not the actual positions. I'm telling you somewhere in this plane on the upside, NG will lie, and somewhere on the down, SG will lie.
Okay, sir.
Okay,
Okay, sir.
so anyways, so this is it, guys. We are done with the this thing, the Earth's magnetism. Let's discuss one more thing which is called as tangent galvanometer. What is a tangent galvanometer? uh, I'll try to show you the diagram. Tangent galvanometer. Copy image. Can everyone see a diagram over here, guys? Can you see a
Yes,
tangent galvanometer over here? Can you see the
yes, sir.
two surfaces? This is a tripod. These are the 2 points where you make the connection, right? I'll try to download the diagram for the experiment as well. Copy image. Ha. And I suppose it's rather complicated. I have to make it simple. Tangent galvanometer experiment. Copy image. Yes, guys. Can everyone see a whole circuit? Don't forget. Just forget this part. Don't. No need to see this part. Okay. So basically, what I have a tangent galvanometer, and can you see a tangent galvanometer over here? Everyone, is
Yes, sir.
everyone able to see a tangent galvanometer over here? I'll try to draw a simpler experiment. So suppose this is a tangent galvanometer, and these are the two plus and the terminals. This is plus, this is minus. That's it, right? And I'll connect this tangent galvanometer to a rheostat. Everyone knows the circuit diagram for a rheostat. So this is a rheostat. Then there is a battery. So then there is an ammeter over here. So ammeter ka plus either minus either. This is an ammeter to measure the current flowing inside. And let us connect it to a. So everyone can see over here plus and this is minus. Sorry, this will be plus and this will be minus. And the current will flow in what direction? The current will flow in this direction, right? So Guys, everyone able to see this tangent galvanometer, right? Guys, hello.
Yes, sir.
Just let me rearrange it, please. You don't need to draw it, Anna. Don't worry. Don't draw it. So, guys, everyone can see there is this vertical stand inside a. There is this vertical coil, and this coil is mounted on a stand. Okay. This vertical coil contains several turns of copper. Generally, the number of turns will be given to you. Let's say 1,000 turns. And even the radius is given to you. Generally, the standard size is the radius of this coil is basically 10 centimeters. This is the standard size. Okay. So basically, inside this coil, there are large number of turns of wire, and the radius of this coil is how much? The radius of this coil is how much? 10 centimeters. Okay.
10 centimeter.
Now, this coil, isko jaise, if you hold a bucket, you understand how exactly do you hold a bucket? The handle of the bucket, is it like this only? No. So suppose if this is the bucket, this is the handle, then you hold it like this, right? Yes or no?
Yes, sir.
So just hold this coil like that, and if you rotate your hand, then this coil can rotate about this axis, right? Can you see this is the stand which I was talking about? And can you see when I'll try to rotate it, this whole thing can rotate? Yes. Okay. Is one component clear, guys? Now inside this there is a magnetic needle. Is everyone able to see a magnetic needle? Can you see this magnetic needle inside? Yes or no? Is everyone able to see this magnetic needle?
Yes, sir.
So I think the
Yes.
construction part is pretty much clear to you. Only that part is important. Rest everything is not that important. Now,
What is the significance of it rotating?
significant. I'll tell you, why it is used, where it is used, and what is the significance of the rotating. Sab aayega. Don't worry. Is the construction part pretty much clear?
Yes, sir.
This vertical coil can rotate about a vertical axis passing through its center. Please remember, when this will rotate, this is not rotating. Hai na? This magnetic field, magnetic needle is stationary. It will always remain like this, but this coil can rotate. So this is how we have constructed it. What is the use of this tangent galvanometer? It is used to measure the horizontal component of Earth of Earth's magnetic field at any point on Earth's surface. So basically, this device का समझ में आया? What is the use? It is used to measure the Earth's magnetic field. Now, how do we do it? Steps. The first step is, wherever you want to find out the magnetic field. First of all, tell me, if you place this tangent galvanometer at any particular point on the Earth's surface, where will the needle point towards?
The magnetic north.
No, on the surface of Earth. Yeah, I know, on the surface of Earth, but it points towards the magnetic needle. We just wrote this particular thing. If the object moves on the surface of Earth, the magnetic needle will point towards the
Okay,
horizontal
horizontally.
component. So basically, the magnetic needle will align along BH, right?
Yeah.
Okay. So the first thing is ki wherever you want to find out the value of the horizontal component, place the tangent galvanometer at the point where BH has to be calculated, right? Now after this, what will you do? As soon as you've done that, the needle will point in the direction of BH. Will the needle point in this? Yes or no? Will the needle, don't need to write the steps, guys, just understand, don't write the steps at all. So place the tangent galvanometer जहाँ पे BH calculate करना है, then the needle will start pointing in the direction of BH. Yes or no? If it starts pointing in the direction, then rotate the coil such that it aligns itself in the direction of BH. I told you, you can align this coil. So suppose when you see the coil from the top, does it look like this? Guys, when you see the coil from the top, does it look like this? And let's say, suppose at any particular point, this is the magnetic needle, then the magnetic needle, let's say it is pointing like this. If the magnetic needle is pointing like this, then what will you say? This is the direction of horizontal component of magnetic field. Can you see initially your coil is not in the direction of BH, right? So basically what will you do? You will hold this coil from here and you will rotate it. When you will rotate the coil in such a way that the coil aligns in the direction of, so now can you see over here, guys, the coil has aligned itself in the direction of the magnetic needle, and we have aligned it, right? Yes or no, guys? So
Yes, sir.
is this step clear? What exactly am I doing? So I think this step is pretty much clear to you. This is the initial state, and let's say this is the final. Okay. All these steps 1, 2, 3, they are done when the switch is open. The steps 1, 2, 3 are basically done when the switch is open. Where is the switch? Here. Can you see when no current is flowing in this direction, I arrange the tangent galvanometer in such direction, right? Now tell me what will happen when I close the switch. As I close the switch, a current starts flowing through the battery, right? Yes or no?
Yes, sir.
And due to this current, if suppose this is the coil, so inside this coil, what will start happening? A current will start flowing. We can measure the current on this ammeter, right? So when key is closed, the current starts flowing into the coil. So now the fourth step is close the key. Once you close the key, what happens? Now a current starts flowing through the coil. Yes or no? will a current start flowing through the coil? Are yes or no? So let's say a current
Yes.
is flowing in that direction, due to which the magnetic field, will this coil also produce certain magnetic field? Due to which coil also starts producing magnetic field of its own. So basically, suppose this is the case, control C, control V, and let's say this is the direction of coil. This was the direction of BH, initially BH, right? And now the coil also starts producing a magnetic field. So what will this needle do now? Will the needle remain in the same direction? Will the needle remain in the same direction? Guys, tell me, will the needle remain in the same direction? No, right? Due to this
No.
particular thing, the net magnetic field due to them will be in this particular direction. So what will the needle do? The needle will also try to align itself along this net magnetic field. Is my point clear till here? So when this B net is there, the needle also tries to get aligned in the direction of BH. But can you see our coil, which was there, we have not moved the coil at all. So the coil is still in that direction only. Yes or no? Is the coil still placed in that direction only? Yes or no? Can you understand this particular thing till here, guys?
Yes, sir.
After this, what I will do, I'll vary the current till the time the angle between this coil and this needle is 45 degrees. Right? Sir, what is so special about 45 degree? At 45 degree, what will happen? This BH and this B coil will become equal, right? Yes or no? We know this particular thing, no? Okay, when both of them are equal, then only the angle between them is 45, 45, right? When both the components. Yes or no, guys?
Yes, sir.
And
Yes, sir.
we have the instruments to calculate the value of B coil. So here the BH at this particular time, will it be equals to mu naught Ni by 2 pi? Huh? Will it be equals to this? So what is the magnetic field at the center of a ring? Magnetic field at a center of a coil is given by 2 pi I by R, and if it has n turns, then n, right? Everyone remembers the formula?
Yes, sir.
So can you see from here, it is equals to mu naught Ni upon 2. Yes? Yes or no? So we know the number of turns. We know the current which will measure in the ammeter. We'll measure the radius as well. We have the radius as well. So can you see from here, I can calculate the horizontal component of it. Yes or no? Is tangent galvanometer pretty much clear to everyone? So this is the concept on which the tangent galvanometer works. We know the value of R. R and N measure I in the ammeter. And if you can measure the value of I in the ammeter, automatically you can measure what? Automatically we can measure the horizontal component of Earth's magnetic field at that point. Is this clear? समझ में आया पूरा experiment क्या था? Guys, did you understand the whole experiment? Shall I show you a video of this? Guys, shall I show you a video of this? It's fine. Everyone understood what is there to be done basically.
Sir, can you please scroll down?
And scroll down.
Thank you, sir.
So this is all about tangent galvanometer and Earth's magnetic field. Okay, let's start doing some questions. At a point on Earth's surface, BH they have given is 40 microtesla, and angle of inclination 30 degree, and they have asked find the total magnetic. Easy है, जल्दी करो.
So is it 80 microtesla?
It is 46 microtesla. Beta, you know this particular thing, no? BH is equals to BE cos theta, right? Did you swap
yes,
it?
sir.
Did we swap it?
Yeah, oh, I think I substituted the theta wrong. Okay.
Okay. So from here, BE will be equals to BH upon cos theta. So cos theta. So this will be 40 micro Tesla divided by cos 30, and cos 30 when you value you will write as root 3 by 2. So when you will write root 3 by 2 and calculate, this will come to be 46 micro Tesla. Okay. Next question. This question is good. A short magnetic, a short magnetic, a short bar magnet is placed in a magnetic meridian. If it is placed in the magnetic meridian, then with its north pole pointing towards south. So its magnetic moment is 0.2 ampere meter square. The neutral point. Achha, what is the neutral point, guys? When we talk about magnetic fields and electric fields, what is the neutral point basically? What is the neutral point where the net magnetic field is?
0.
0. Yes. the main key is to draw a diagram. Can you see north, south, everything is involved. So let us say this is your magnetic meridian, suppose. At that particular point, let's say this is the magnetic meridian. And inside this magnetic meridian, if I denote certain points, let's say this is the north, this is the south, this is the east, and this is the west. Okay. Yes or no, guys? Everyone able to see this magnetic meridian plane, right? Everyone is able to see this plane. Now they have said this particular thing ki they have a bar magnet whose north is pointing towards the south. Yes or no? Is it like this? Can you see the north is pointing towards the south and south is pointing towards the north? Yes or no? Is the first statement clear?
Yes, sir.
Can you see they have given its magnetic meridian with its north pole pointing towards south? So if this is the case, then what will be the direction of magnetic moment? The magnetic moment will be, can anyone tell me what will be the direction of magnetic moment? The magnetic moment will be in this direction. Yes or no? And they have said very clearly, Acha, its magnetic moment is this much. The neutral point is obtained at 10 centimeter from center of magnet towards north. So basically from the center of magnet 10 centimeter towards north, there is a point on the axis of the magnet. This is that point P, where they have obtained what? A neutral point. Yes or no? First of all, can
Yes, sir.
anyone tell me what will be the direction, what will be the magnetic field is acting at this particular point? What will be the direction of a horizontal component of Earth's magnetic field at this point, because it's on the surface? So can anyone tell me what will be the magnetic field, a horizontal component of Earth's magnetic field, and in what direction will it act? Will the horizontal component of Earth's magnetic field point towards north? So will it be like this? Yes or no? We know that the horizontal component of Earth's magnetic field points towards the north direction, right? Yes or no? And can you see this is a dipole, and on the axis of the dipole, this magnetic field is in the same direction of dipole moment. So can you see the magnetic field due to the magnet is in the same direction of the dipole magnet? Horizontal component of Earth is acting toward north-south. So can you see very cleverly we mixed the two concepts of what we discussed in magnetism, right? Yes or no?
Sir,
Once
so
more.
but I didn't get, yeah, how BH is like to the north.
Because we always know, no? अरे मेरे को एक बात बताइए. If I have a magnetic needle, will it align itself in what direction? It always align itself in
Okay.
north-south direction, right?
North.
So
Yes,
that
sir.
implies the direction of horizontal magnetic field is also in the same direction.
Okay.
So it's like this. Okay.
Okay, sir.
So BH ऊपर की तरफ है and B magnet is towards down. So can you see the neutral point? What will happen at a neutral point? B net is 0. The B net is 0. So basically, can you see over here, magnetic field and the Earth's magnetic field, they should cancel out each other, and hence they should be equal, right? And from here, you can calculate what is the magnetic field of a bar magnet, very small bar magnet, and 10 centimeter is the distance, axial position, twice of km by r cube. Everyone, do you remember this formula? Dipole. That will be twice of k will be mu naught by 4 pi, and the value of mu naught by 4 pi is 10 to the power minus 7. M they have given 0.2. R they have given 10 centimeter, that implies 0.1 whole cube. Sir, why are you using this formula? Because the bar magnet is small. So when I calculate this thing, this will be 0.2 into 0.4 into 10 to the power minus 7, and this will be 10 to the power minus 3. ये कटेगा, minus 4 will remain, and if I give 2 more zeros, so for 40 micro Tesla, that is the answer. Clear? Please note it down. The next question you need to do it by yourself. Done, guys.
Yes, sir.
Yes, sir.
Mhm. The radius of a tangent galvanometer. Everyone understood the concept of tangent galvanometer, right? The radius is
Yes, sir.
16 centimeter. Okay. Now, the question is, find the number of turns in the coil if a current of 40 milliampere produces a deflection of 30 degree in it from the magnetic meridian. अच्छा हाँ, एक बहुत important point I forgot to tell you. Sir, what was the point of rotating the coil in the direction of this particular thing? When you do this, no, guys, can you see over here the coil, the plane of the coil? Is it the magnetic meridian at that point? So basically, by rotating the coil, what exactly we are doing? We are aligning the coil in the direction of the magnetic meridian, right? Hello, guys, you understood this point? So by aligning
Yes,
this
sir.
coil, we are rotating it in the direction, or basically we are aligning the coil in the direction of the magnetic meridian. So basically, this 30 degree is basically not that by which you are rotating. This 30 degree is basically this angle. Can you see here the angle was 45 degree, 45 degree, right? So when a current was passing through this particular thing from the magnetic meridian, the needle deflected by 30 degree, right? So please remember this particular thing. Acha. And also they have given BH is equals to 36 into 10 to the power minus 6. So suppose at this particular point, this is your BH, and when you applied the current, the coil, magnetic field due to the coil was like this. And can you see the needle will arrange itself in the direction of the net magnetic field, right? So this angle was basically 30 degrees. Okay. Is this clear, guys? Can you form this thing? If you can form this thing, then this question is over. Can you see from here this BH, and what is the relationship between BH and B coil? Can I draw it like this? BH over here, B coil over here, and the net will be like this, and this angle will be 30 degree, right? Can I draw it like this, guys? If I can draw it like this, then can you see a triangle? If this angle is 30 degree, then automatically this angle is also 30 degree. So from here, B coil upon BH is basically tan 30 degree. So from here, B coil is equals to BH into tan 30, right? In the previous case, it was BH into tan 45. So that's why B coil and BH were equal, right? If they are making at certain angles, then you can do this. Now I am not doing it. You can calculate the magnetic field due to a coil, and then you can find the number of turns. Start with I need the answer. And give me 2 minutes. I'll be just back in 2 minutes. Done, guys.
Hey man, then what issue you're getting now when you're trying to upload the document now?
B coil will be equals to what?
What exactly issue you're
Mu naught Ni by 2R is equals to BH
getting? Yeah, okay.
tan 30. So from here I can calculate number of turns. BH tan 30 into twice of radius divided by. Did I give the radius also?
It's 16 centimeter.
Okay. Into divided by mu naught N. Oh, sorry. Mu naught into Y. Right? So I can calculate this. Horizontal magnetic field is given as, horizontal component is given as 36 microtesla. Tan 30 is 1 by root 3. 2 is 2. Radius is 16 centimeter. Can you see I'm writing everything in SI? Divided by mu naught की value I will write as 4 pi into 10 to the power minus 7. And current was how much? 40 million. So I think it is calculatable, right? When we'll do it, the answer will come at approximately 132 tons. Okay. Is this clear, guys? So questions, all of the questions are clear, right?
Yeah.
Chalo. So these type of questions will be generally formed on terrestrial magnetism. Let's discuss next point, which is magnetic properties of material. Let's discuss the magnetic property of material. So based on the response of a material when placed in an external magnetic field, materials can be classified into three different types. Materials can be classified as diamagnetic materials, paramagnetic materials, and ferromagnetic material. There is one more which is called as ferrimagnetic material, but it's not there as a part of our syllabus, but I'll still give you definition somewhere. So anyways, we know this particular thing. Guys, do we know this? That whenever a charge is rotating around a nucleus in a hydrogen atom, if a charge is rotating around the nucleus, right? So suppose if this is an electron and this electron is rotating with the speed v, then we know this particular thing. Guys, hello? Guys,
Yes, sir.
does everyone you know this particular thing? We can assume it to be what? We can assume it to be a equivalent current. किसी को याद है क्या? किसी को याद है? You can assume this to be a equivalent current which is flowing in a circuit. If electrons are flowing anti-clockwise, then current will be flowing clockwise, right? What will be the value of this particular thing? Suppose if it is going with V, then V is equals to R omega, and omega is basically equals to what? V by R. And we also know this particular thing, omega is nothing but 2 pi by T. So from here, T will be equals to 2 pi by omega, and I can convert it into form of V and R, right? Yes or no? We already know about this particular concept, and we'll discuss this concept more in modern physics. Then we'll be doing the last chapter, no? Atomic structure. It's not the last, it's somewhat, So in modern physics, we'll be doing this chapter, atomic structure, where I'll teach you this thing in detail, where exactly the formula is there. And so can you see over here, when current will be produced due to this current, what will be the direction of magnetic field? Due to this current, there will be certain magnetic field. Yes or no? Some magnetic field will be there. And can you see if this is the magnetic field produced at this particular point, then can you see this small atom which was through which this hydrogen, this electron was revolving? Will it behave as a magnetic dipole? Will it consist of any magnetic dipole, right? The magnetic dipole will be equals to what? N into I into A. Do you remember this?
Yeah.
And also basically I can assume this particular thing ki whenever there is a atom in which the electrons are orbiting, then that will behave as a magnetic dipole. ये अपने को पहले से ही पता है. An atom in which electrons are revolving around nucleus behaves as a very small magnetic dipole. ये कंसेप्ट सबको पता है? बोलो हाँ.
Yes.
Write down the heading. Acha, by the way, whatever this magnetic moment is it natural, right? It's not man-made, no? We have not created this particular thing. So, natural magnetic moment. Acha, please remember, when it will behave as a very small magnetic dipole, then it will have certain magnetic dipole of its own. I'm not writing that point because that point is understood. Hai na? If it is a magnetic dipole, then automatically it will have certain dipole moment. Hai na?
Yes, sir.
Now we know this particular thing in different materials. There are different orbits, right? There are different orbits, and in these orbits there are many electrons which are revolving around the nucleus. Yes or no? So can I say this particular thing ki each atom inside a material has a very or can I carry as certain dipole moment of its own due to electrons spinning around nucleus. Yes or no? So based on this dipole moment, there are various possibilities, right? The first possibility is when suppose this is a block, and let's say this is basically what? These are the atoms. Can you see over here? These are the atoms. Okay. So suppose this is any solid material, and these are basically your what? These are your atoms. Then can I say uh, individually, it is not necessary that always this electric dipole moment will be there. There will be certain materials where this atom, there will be certain materials in which the lattice has zero magnetic moment. Yes or no? Can I say this particular thing? There will be certain materials in which the lattice atoms has zero magnetic moment, because can I say this thing? There are many electrons revolving in different orbits, producing magnetic moments, producing individual atomic dipole moment in different directions at random, right or wrong? So whenever these atoms will be producing different then what will happen? Different direction at random.
They cancel out.
So it is possible that all atoms, or is it possible that the net dipole moment of can I consider this?
Yeah.
So this is one of the theory which is possible. You can also say that suppose the individual, this is one theory which is basically what, कि individual atoms की वजह से zero हो गया तो overall भी zero है, right? The second theory says that if I have any material, and if I consider कि yes, individually it has certain individually the dipoles are there, and these dipoles are arranged in random direction. So in the first case, what was the difference between the first case and the second case? I'm telling you. In the first case, individual atomic dipole moment is also zero, and overall dipole moment is also zero. In the second case, what am I saying? That individual atomic dipole moment is non-zero, but still overall dipole moment is equals to 0. Why? Because these individual dipoles, they are randomly oriented, right? So can I say these two types of material, right? There can be a third type of material where the individual atomic dipole moment is also there.
Wait, so what's the difference between the first and the second case?
The first and the second case is basically individual atomic moment is also 0 and overall is also 0. Second will be the case where individual is not 0, but since they are overall randomly oriented, then what will happen? Overall is also 0. Third will be the case where individual is also not equal to 0 and overall is also not equal to, right? So this material will have certain total magnetic moment of its own. Yes or no?
Yeah.
So is it clear, guys? In the natural magnetic moment, these are all different possibilities they exist. Individual can also be 0, overall will be 0. Individual cannot be 0, but still overall can be 0. And third is individual cannot be 0 and overall is also not equal to 0, right? Because there will be certain, so these are three different types in different materials, right? Next,
So how is the individual 0 in the first one?
first वाले case में, because there are many electrons, no? Is it necessary? It's always a single hydrogenic atom. नहीं ना, बहुत सारे atoms होते हैं. All of them are revolving in different orbit. They have different spin angular momentum, right? तो ऐसा भी हो सकता है कि cancel out हो जाए.
Electron will cancel out. Okay.
Yes. So there will be overall dipole moment. So yeah, these are all the different possibilities which we have, and based on this we have different types of material, right? This second and third theory is much more, these materials are much more commonly found as compared to the first ones, because the first ones are like very ideal case. So generally any material which you will found, you will find it like they will either have dipole moment, the overall dipole moment, or they will not have dipole moment, right? So these 2 and 3 are most commonly found in nature, whereas 1 is very rare. Now let's start one by one about various possibilities. I told you about this particular thing. We'll discuss about diamagnetic and paramagnetism. So let's start with diamagnetism. Please write, it is a property due to which a material has a tendency to repel the external magnetic field in which it is placed. So basically whatever external magnetic field you are applying on it, this material will try to do what? Repel the magnetic field of its own. Okay. So for example, suppose there is a coil. I'm trying to make you understand, this is not a diamagnetic block, this is just a coil. Okay. And suppose you are moving this magnet, in which what is the direction of B external? Can you see magnetic field will be coming out, right? Hello?
Yes, sir.
Anna? So tell me this particular thing, if I move this magnet towards the coil, then what will happen? What will happen towards the, if I move it towards the coil? The coil will generate a current in such a way that the coil will induce the coil will oppose the external magnetic field according to Lenz's law, right? Yes or no?
Yes, sir.
Yes, sir.
Initially, when magnet is not moving, then the magnetic dipole moment of coil, can I consider it as zero? If initially, if the magnet is at a very large distance away from it, then coil will have no interaction with the magnet, external field, right? Initially, magnet is far away. So can I consider this, the initial magnetic dipole moment is zero? Now what will happen when magnet is brought close? A current is induced in it which opposes the external magnetic field. Yes or no?
Yeah.
According to Lenz's law, in accordance with
Lenz's law.
right. So in accordance with the law principle of electromagnetic induction, what will happen? Now due to this, can you see over here, if the magnetic field of the coil is coming in that direction, then can I say a north pole will be developed over here side, or this side will be the south, right? So can you see, if a north pole develops, can you see the magnetic moment of this coil is in this direction, right? Yes or no? Can you see a magnetic dipole moment getting induced in this direction? So is it, can you see over here, this north and this north, they both repel each other. This north and that north will repel each other, due to which what will happen, the magnet will also experience a force which will try to be away, and this will also experience a force which will try to move in this direction, right? Yes or no? So we can say this particular thing, due to the magnetic field induced, we can say a magnetic dipole moment is induced in the coil and due to this dipole moment, and please remember this dipole moment is induced, due to this induced dipole moment, the magnet and the coil repel each other with a force. So concept समझ में आया?
Yeah.
Okay. So with a force. So basically what will happen, if suppose the same concept, if I have a diamagnetic block, this is a diamagnetic block. Initially this diamagnetic, what is the initial dipole moment of this diamagnetic block? Initial dipole moment is, so Mi is 0. Yes or no?
Yeah.
But as soon as you place it in an external magnetic field, as soon as we'll place it in an external magnetic field, inside these atoms, small, can you see small loops are there? Some dipole moment will be induced in these, can you see there will be coils, right? So due to this particular thing, certain dipole moment is induced in every atom in the direction opposite to the external magnet. So basically what is this?
Okay.
These are basically the direction of induced magnetic moment inside every atom. And can you see over here? Here, when a diamagnetic block is placed, how much time is left? The time is over. So we'll just write this statement, and we'll write some more points in the next class. Okay. So when a diamagnetic block is placed in an external magnetic field, then every atom induces a magnetic dipole which opposes the external magnetic field, and the block starts repelling the magnet. Yes or no? So due to which what will happen? This will be subjected to a force in this direction, and this will be subjected to a force in this direction. Yes or no? So can you see this diamagnetic coil is exactly behaving just like a coil? So that's why we use the concept of, I taught you the coil, what exactly is happening in coil, and then we use the concept of that to prove the same thing is happening in the case of a diamagnetic substance. Is this clear?
But sir,
Hanji?
if we take the magnet away, won't it attract it?
It will attract.
Yeah,
It will
then
attract.
won't the properties be reversed?
नहीं, properties won't be reversed. बेटा अभी यहाँ पे देख external magnetic field को you are indicating, but यहाँ पे just pay attention for this particular thing. यहाँ पे magnet जो है is basically what? The magnet is basically doing what? यहाँ पे अपना increasing magnetic field है ना?
Okay.
यहाँ पे since
You only consider that case, you're saying.
we can, हाँ मतलब you can, I think you might have read this property somewhere. Diamagnetic materials are easy to magnetize and demagnetize. ऐसा पढ़ा होगा तुम, पढ़ा है क्या?
So if you take it away, it gets demagnetized.
Demagnetize, तो फिर वो demagnetization का concept अलग place में हो जाता है.
Okay, fine. I get it.
Starts repelling the magnet anyways. Please remember, diamagnetism is a very weak phenomena. Diamagnetism, it is a very weak phenomena. And almost every material has a diamagnetic character in it till some extent. So please remember, even if the material is paramagnetic or ferromagnetic, doesn't matter, still it will possess the property of diamagnetism, क्योंकि ये उनका जन्मसिद्ध अधिकार है to oppose the change in the magnetic flux, because this is what Lenz said, right?
Yeah.
Oppose करना उनका हक है, but वो opposition strong है या small है, that all depends upon the material, right? So please remember, so if some dipole moment is there initially, so if suppose if initially certain dipole moment of the material existed, then the induced dipole moment will oppose the initial magnetic moment. But this opposition will be small. याद रखना है ना? So diamagnetism is a very weak phenomena. Don't over stress on it, है ना? ज़्यादा दिक्कत नहीं है. So this is all about diamagnetism. In the next class, I'll start with paramagnetism. Okay, and we'll be done with all the properties. Okay, guys, we'll be discussing
sir.
all the properties and we'll be done with this chapter. Even the hysteresis loops and all. Once you are done with diamagnetism, then understanding para and ferro is very easy. Is this clear? Don't worry, I'll give you it. Give it the differences between paramagnetism, diamagnetism, ferromagnetism in a tabular format, where you can differentiate between them in the notes which I'll provide now. There. Chalo. So that's it for today's class, guys. Thank you very much.